Hello, my name is Elyas Masrour, and I'm here today to talk to you about a project conducted by myself, Neil Sorkin, Samantha Falco, and Dr. Paul Jaffe. We are a space solar power team at the University of Maryland and are presenting our project, Automated Health Check for Space Power Satellite Systems. So, what is space power satellite systems? Well, it's no secret that we're facing a climate crisis and imminently need to find ways to generate electricity that doesn't irreparably harm our environment. One of the leading candidates in this search is solar power, a concept you're likely familiar with. We are today putting large solar panels on roofs, houses, and in large fields to catch energy from the sun and convert it to clean power. But there's a big obstacle with current solar power collection methods. Unfortunately, the sun doesn't always shine. There are clouds and there is nighttime. Humans being humans, we use power 24 hours a day, 365 days a year. A possible solution to this is the concept of space solar power. Now, this idea was first introduced in the 1970s as a way to address climate change. And it's sort of simple. We can put our solar panels in space. Satellites composed of large arrays of photovoltaic panels set in orbit around the Earth can collect undisturbed energy from the sun and then beam that energy back to Earth via a laser beam or as RF power. Deploying solar panels in space has many advantages, including no size constraints, no losses due to the atmosphere or weather events, and the ability to generate clean energy from the sun 24 hours a day. But there are also many challenges associated with space solar power. Namely, these systems would be very expensive to implement, are untested, and could be costly to repair. Another factor we must consider is the CO2 released in the process of manufacturing, transporting, deploying, and repairing these systems. A concept developed through one of NASA's innovative advanced concept studies, titled Solar Power Satellite via Arbitrarily Large Phased Array, or SPS alpha, will be used as the configuration for our proposed solution. SPS alpha is a modular solar power satellite with 5 main parts: a sunlight reflector system, a photovoltaic collector system, a DC to RF converter, a phased array to beam the RF or microwave energy back to Earth, and a rectifying antenna to finally convert that energy to usable energy on Earth. In the event that one of the reflectors or photovoltaics is damaged by space debris, solar flare, or other event, the efficiency of the entire system is lowered. Lowered system efficiency limits power yield beamed back to Earth and requires power to be sourced from other, potentially non-renewable CO2 emitting sources. A system capable of detecting damaged reflectors and photovoltaics and reporting it back to be replaced could maximize solar power satellite efficiency and keep the system running in optimal order. Because the CO2 cost is so high, it is essential that we maximize efficiency over the entire lifespan of the system. Our innovation is targeted at doing just that. An automated health check system is hard to generalize for all SPS, so we're going to stick to SPS Alpha Mark II when describing our system. We want to track the health of the reflectors and the health of the photovoltaics, but first let's define what we mean by health.
Here is a diagram of how a typical SPS system is designed. A reflector is in good health if it reflects as much light as possible towards the solar cell. An example of an event that would lower its health is a micrometeoroid impact. A hole through the surface of a reflector could cause a slightly lower reflectance level, as that particular area where the hole was made is now not able to reflect light. If a small hole is made, it might not make sense to replace the entire reflector or repair it at all. On the other hand, if a large rock came through and made a big hole in the reflector, we might want to replace it because it is taking up space that could be used for a fully functional reflector. Now onto photovoltaics. A photovoltaic is in good health if it is able to convert the reflected sunlight as efficiently as possible. A micrometeoroid impacting a photovoltaic might be more damaging to the overall functionality of the system because you lose the ability to convert concentrated light at that point, whereas an equally sized damage area in a reflector loses only that amount of area of unconcentrated light. This means that we should value health checking for equal areas of photovoltaics more than reflectors. Now, how do you actually determine the health of each of these components? Again, we will begin with the reflectors. Here is a rendering of one of the reflectors on the SPS alpha system. Using a LiDAR-like system, we can determine if at any given point a reflection is detected. We can create a daily polar coordinate map of the intensity of a bounced laser at any given point on the reflector. For a working reflector, we expect most of the light to not return, but for a dysfunctional reflector, the light could reflect back. This would indicate that the reflector is not oriented at the photovoltaics properly at that point on the reflector. At the center of each of the reflectors lies a solar cell configuration needed to power the LiDAR unit. Within the center of each of these reflectors could also contain a computer necessary to store and process the data provided by the LiDAR unit in the middle. An added benefit of using solar panels on each reflector is to ensure no single point of failure for all detectors, such as a centralized power source. Each day's data will be stored within each reflector and compared to the previous day. Only if a deviation from normal is detected should a given reflector send a wireless signal to a control module to beam a message to Earth that a hole was detected. The damage can be confirmed using a pan, tilt, and zoom camera positioned on the backbone of SPS alpha. To track the health of the photovoltaics, we can simply track the energy generated by the panel at any given time and compare it to the day before at the same time to match the expected orbit. At the same time also, we can take a snapshot of the entire photovoltaic array. This could be done once an hour. This way we can keep a log of what each of the photovoltaic cells looked like at any given time in orbit for reference. Then, if we detect an anomaly, which is defined as an unexpected loss of energy relative to the previous day at the corresponding time, or a drop relative to their photovoltaic cell neighbors for a given time, then we can do a pixel-wise comparison of the day before and the current image. If a significant difference is discovered, it is reported to Earth, along with a picture of the potentially damaged photovoltaic. To limit the launch weight and CO2 impact of replacement missions, maintenance will be performed robotically. The existing design for the SPS Alpha already includes modular push-pull robotic arms, which may be adapted for reflector maintenance purposes.
We did some experimentation to prove our concept. Take a look. We wanted to prove that a shined laser could determine the difference between a healthy reflector surface and a non-healthy one. For our healthy surface, we used a makeup mirror commonly available in many convenience stores. For our non-healthy surface, we used a lotion bottle that was semi-reflective. We set up our small demo with a black curtain to represent space and our reflector surfaces lying near the bottom. From a safe distance and with proper safety precautions like safety goggles, we shone the laser towards the surface. As you can see, with a healthy surface, the amount of light that shines back is minimal. On the other hand, with a non-healthy one, there is a lot of reflection. When comparing these visuals, we can easily see the difference. Modern computer vision software can easily automate this differentiation, and so our concept appears to work. So, in the end, this is our proposed concept of how to automatically monitor space-based solar power systems for potential damage. In reality, these systems are an extraordinarily difficult engineering task. There are so many parts of this system that need to be designed and validated, and there's a lot of new technology that we still need to create. This project is one small aspect of a space solar power system, but in our opinion, a critical one. However small, it's just another step towards a large and complicated system that may, one day, change how we collect energy for the better. Thank you for watching.